Welcome to the week 7 of Swayam course on Introduction to Electric Vehicles and Hybrid Electric Vehicles. Last week, we explored energy sources such as fuel cells and storage systems like batteries, ultracapacitors and flywheels. This week, we will delve into various types of electric motors employed in electric vehicles, examining their distinct characteristics and applications. We will also explore the principles and technologies behind the motor control. By the end of the week, you will have a comprehensive understanding on how electric motors are managed to optimize the performance and efficiency in EVs. Electric motors are essential components in electric vehicles because they are responsible for generating the power necessary to move the vehicle's wheels. Unlike traditional internal combustion engines, which rely on burning fuel to create mechanical motion, electric motors utilize electrical energy stored in the batteries. This electrical energy is converted into mechanical energy, which then drives the wheels of the vehicles. Normally, 4 types of electric motors are used in the EVs. They are induction machine, permanent magnet synchronous machine, brushless DC machines and switched reluctance machines. Now we will see each type of machines that are used in the EVs. First we will start with the induction machines. Induction motors are commonly used in many electric vehicles. They operate on the principle of electromagnetic induction, where an alternating current in stator creates a rotating magnetic field. This field induces a current in the rotor, producing torque that turns the motor shaft and drives the wheels. The squirrel cage induction machine are most commonly used in EVs. Next, coming to the permanent magnet synchronous machines. The permanent magnet synchronous machines use permanent magnets embedded in the rotor to create a magnetic field. These motors are highly efficient and provide high torque at low speeds. They are widely used in modern electric vehicles due to their high performance and efficiency. Next, coming to the brushless DC machines. The brushless DC machines operate on direct current but have no brushes, making them more reliable and requiring less maintenance. They use electronic commutation to switch the current flow, which reduces wear and tear and improves efficiency. These motors are known for their high power density, efficiency, making them suitable for various EV applications. Next, coming to the switched reluctance motors. Switched reluctance motors have a simple and rugged construction with a rotor made of soft magnetic material and no windings or permanent magnets. The stator has coils that are sequentially energized to create a rotating magnetic field, causing the rotor to move. They are known for their robustness, simplicity and high efficiency over a wide range of speeds. Electric motors are pivotal in advancing the performance, efficiency and sustainability of electric vehicles. Each type of motors offer unique advantages, contributing to the overall diversity and innovation in EVs. Now we will discuss in detail about each motor. First, let us start our discussion with the induction machines. Now we will see the fundamentals of the induction machine starting from the construction. Now, if you see the basic induction machine, we have the stator and rotor. The stator is the stationary part of the motor and contains the windings connected to the power source. It is made up of laminated steel sheets to reduce energy losses due to eddy currents. The windings are arranged in such a way that they create a rotating magnetic field when an alternating current passes through them. Next, coming to the rotor is a rotating part of motor and is placed inside the stator. It is also made up of laminated steel and can be of 2 types. One is squirrel cage rotor and second one is wound rotor. The squirrel cage rotor consists of aluminum or copper bar short circuited by end rings resembling a cage. It is simple, rugged and commonly used. Wound rotor. Wound rotor have similar windings to the stator windings connected to external resistors via slip rings. It is used in applications requiring high starting torque and controlled speed. Next, coming to the working of induction machine. In an induction machine, applying a 3-phase AC voltage source to the stator windings, which are spaced 120 electrical degrees apart, generate 3-phase currents in these windings. These currents create a rotating magnetic field in the air gap. The speed of the magnetic field created is directly proportional to the frequency of applied AC voltage. When the rotating magnetic field interacts with the rotor conductors, EMFs are induced in accordance with the Faraday's law. These induced voltages generates currents in short circuited conductors, producing torque on the current carrying conductors within the rotating magnetic field. As a result of this torque, rotor begins to rotate in the same direction as the rotating magnetic field. The stator windings are supplied by 3-phase AC sinusoidal currents. Let us assume the magnitude of current is Im amperes and the angular frequency of current is omega radians per second. Then the 3-phase currents can be expressed as IAS equal to Im cos omega t, IBS equal to Im cos omega t minus 120 degrees and ICS equal to Im cos omega t minus 240 degrees. Each of these 3-phase currents will generate a magnetic field. Let BA, BB, BC be the magnetic field generated by the currents IA, IB, IC. BA equal to K into IAS of cos omega t, BB equal to K IBS of cos omega t minus 120 and BC equal to K ICS cos omega t minus 240. There will be a resultant magnetic field because of these 3 fields, which is equal to Bm cos omega t minus theta. The total magnetic field is sinusoidal field with its peak rotating at an angular speed omega radians per second. Since the omega is equal to 2 pi f, the rotating speed of the field will be same as the supply frequency f revolutions per second or ns equal to 60 f revolutions per minute. In a p-pole motor, the rotating speed ns of the field is given by ns is equal to 2 pi p f into 60, that is equal to 120 f by p. Once the rotor is rotating, the rotor eventually reaches a steady state speed n. This rotor speed is always less than the speed of the stator rotating magnetic field, which is also called as the synchronous speed. The difference between the synchronous speed ns and the rotor speed n is called the slip speed. The slip speed is expressed as a fraction of synchronous speed and is called as the slip and can be defined as S equal to ns minus n upon ns. For obtaining the motor torque, let us consider approximated per phase equivalent circuit of induction machine. Here Rs and XLS are the resistance and inductance of the stator winding, XLR and RR are the inductance and resistance of the rotor winding referred to the stator. Let IR be the current flowing through the rotor, which is equal to Vs by Rs plus RR by S plus J XLS plus XLR. The power delivered through the air gap from stator to rotor is called the air gap power and it is denoted by the term PAG. So, PAG equal to IR square RR by S. The air gap power PAG, that is input power to the rotor, will be dissipated in the resistance of rotor circuit in the form of copper loss and the remaining part is converted into the mechanical output. So, PAG equal to IR square RR, which is the rotor copper loss, plus IR square RR by S into 1 minus S, which is the mechanical output power. So, this mechanical output power is equal to output torque T mech times into the angular frequency omega m. So, P mechanical is equal to T mechanical into omega m. Therefore, the T mechanical is equal to mechanical power output by omega m, that is equal to 1 by omega S IR square RR by S, and this IR is equal to Vs by Rs plus RR by S plus J XLS plus XR. Substituting this in the mechanical torque expression, so Tmac equal to 1 by omega s Vs square by Rs plus Rr by s whole square plus J into XLS plus XLR whole square into Rr by s. So now using this torque expression, we can plot the speed torque characteristics. The speed torque characteristics of induction machine is shown here. In this speed torque characteristics at the low slip region or normal operating region, the torque of the motor is proportional to slip. So as the torque increases, the slip also increases. During the low speed operation, the torque of the motor is inversely proportional to the slip. As can be seen, whenever the torque increases, the slip decreases. From the curve, you can also see that there is a slip at which we have the maximum torque, which is called the breakdown torque or pull out torque. The slip at which this maximum torque is obtained can be obtained by differentiating the torque expression with respect to the slip and equating to 0. Next is the operating modes of the induction motor. First, let us delve into the motoring mode. There are 3 operating modes of the induction machine: motoring mode, regenerative mode and plugging. First, let us delve into the motoring mode, which is prevalent in operational state of the induction motor. In this mode, the rotors rotate in the same direction as stator's rotating magnetic field, albeit at a slight reduced speed. This difference in speed results in what is known as slip, which is defined within the range 0 to 1. Slip is relative speed difference between the synchronous speed and of the magnetic field and the actual speed of rotor. The presence of slip is crucial as it signifies both the air gap power and mechanical power generated by the motor are positive. In the motoring mode, slip indicates that rotor is always trying to catch up with the stator's rotating magnetic field but never reaches it. In the motoring mode, the slip indicates that rotor is always trying to catch up with the stator's rotating magnetic field but never quite reaches it. This continuous attempt creates a relative motion that induces currents in the rotor windings. These currents interact with stator magnetic field, producing a torque that causes rotor to turn. This slip is essential because without it, there would be no relative motion to induce the necessary currents for torque production. The air gap power, which is the power transfer across the air gap from stator to rotor, is a key factor in this process. This power is converted into mechanical power as the rotor turns. The mechanical power generated by the rotor is used to perform work such as driving loads connected to the motor shaft. In essence, during the motoring mode, induction motor effectively converts the input electrical power into mechanical power facilitated through the air gap between stator and rotor. This conversion process is highly efficient and underlines the motor ability to perform mechanical work, making it integral component in various applications where motion is required. The motoring mode is favored in many applications due to its simplicity, reliability and robustness. Induction motor in this mode are known for their durability and low maintenance requirements. Moreover, they can operate in wide range of environmental conditions and are relatively inexpensive compared to the other type of motors. Furthermore, the induction motor's ability to self-start and run without the need of complex control systems add to its widespread use. The motor's performance characteristics such as speed torque characteristics are suitable for many industrial processes. As the load on motor increases, the slip increases, providing more torque to handle the load without significant changes in speed. The efficiency of power conversion in motoring mode also contributes to energy saving and cost effectiveness in industry applications. In addition, the scalability of induction motors allow them to be used in both small scale applications and large industry machinery. Overall, motoring mode is the fundamental operation of induction motor, providing reliable and efficient mechanical power for myriad of applications. Next, coming to the regenerative braking mode. When an induction machine is driven to speed higher than the synchronous speed by an external prime mover, the slip becomes negative. This results in both air gap power, mechanical power becoming negative. This negative slip indicates that power flows from mechanical system into the rotor circuit, then across the air gap to the stator circuit and finally into the external electrical system. In this scenario, the induction machine operates in generation mode, commonly referred as regenerative braking. Regenerative braking may occur when stator frequency applied to the induction machine is lowered to reduce the rotor speed. During this process, due to inertia of drive system, the instantaneous speed of rotor may exceed the instantaneous synchronous speed. This situation results in negative slip, which causes the direction of developed torque in the motor to be opposite to the rotation of the rotor. This opposing torque acts as a braking force that slows down the rotor speed. In this case, motor operates as a generated and generated electric power is fed back into the power source. This conversion of mechanical energy into electrical energy and feeding back into the electric grid constitutes the regenerative braking. The efficiency of this process can significantly improve the overall energy efficiency of the system, as it recaptures energy that would otherwise be lost as heat during braking. This makes regenerative braking particularly valuable in applications such as electric vehicles, elevators and various industrial machinery where frequent starting and stopping occurs. Moreover, regenerative braking helps reduce wear and tear on mechanical braking components, as it supplements or even replaces traditional braking methods. This not only extends the lifespan of components, but also leads to the cost saving and maintenance and replacements. The last mode is the plugging. In the last operating mode of induction machine, where the rotors rotate in the direction opposite to the stator magnetic field, results in slip greater than 1. In this mode, both electrical power from the stator and mechanical power from the rotor flow into the rotor and are dissipated as heat. This dissipation of power can potentially cause rotor bars to overheat due to significant energy biasing converted into significant energy being converted into thermal energy. Despite of the risk of overheating, plugging mode is particularly useful for quick braking the motor. This rapid declaration is achieved by reversing the direction of stator magnetic field while the motor is running. This can be done by switching to any two phases of three-phase windings, effectively reversing the phase sequence. When the stator magnetic field is reversed, the torque developed by the motor now aligns with the direction of new stator magnetic field, but opposes the current rotation of the rotor. This opposition between the developed torque and rotor's rotation creates a strong braking force that rapidly decelerates the rotor. Operating in plugging mode allows for efficient and swift braking, which is crucial in applications requiring immediate stops for safety and operational reasons. However, the intense heat generated in this mode necessitates careful management to prevent damage to the motor components, especially the rotor bars. In practical applications, the plugging mode is often employed in conjunction with other braking mechanisms to balance the need for quick stops and thermal management of motor. The strategic use of plugging ensures that motor can be halted efficiently without incurring excessive wear or overheating. The speed control of induction machine. The speed of the induction motor can be expressed as N is equal to 1 minus S 120 F by P, where the speed of the induction motor depends upon the number of poles, frequency of supply frequency F and the slip S. If you want to control the speed, we can control by using any one of these three variables by changing the number of poles. The stator windings are designed in such a way that by changing the winding configuration, the number of poles can be changed. This technique is used in the past, but in nowadays this is not used because it is very much complex and have low efficiency. Next speed control technique is by changing the frequency. This is most widely used speed control technique. This I am going to discuss in the coming topics. Next, change in slip. The change in slip can be achieved by changing the magnitude of supply voltage. As the supply voltage is changed, speed of motor is also changed. However, This method provides limited variable speed range since the torque is proportional to square of the voltage. Next method is adding the stator resistance or stator leakage inductance. By adding the stator resistance or leakage inductor in series with the stator winding, we can control the slip so that we can control the speed of the induction machine. The problem with this technique is since we are adding the additional impedance in the circuit, there will be associated power losses in the circuit and this is not efficient. As I said, among these three methods, change in frequency for controlling the speed is more popular. Now, if you neglect the drop in the resistance and inductance, the supply voltage is proportional to the flux and frequency. From this, the flux is proportional to the supply voltage by frequency. So, whenever we are changing the frequency, the supply voltage also needs to be changed so that the stator or rotor core will not get saturated. In this V by F control, whenever the frequency is changing during the low frequency operation, the supply voltage is also increased in such a way that the flux remains constant. Since the flux remains constant, even the torque also remains constant in this region. We are going to increase the frequency and voltage up to the base speed or the rated voltage condition. Beyond this, if you increase the frequency, we need to reduce the voltage we need to maintain the frequency constant so that flux reduces. This reduction of the flux is called the flux weakening region. In this flux weakening region, we can go for higher speed in case of the induction motor. This is the most popular speed control technique in induction motor. However, this V by F control method can control the motor torque only in the steady state condition and cannot be used to control the motor dynamic behavior. To control the motor dynamic behavior in transient condition as well as steady state condition, vector control needs to be used. For implementing the vector control, the mathematical model of induction machine is required. To have this mathematical model of induction machine, let us consider a 3-phase 2-pole induction machine. For this 3-phase 2-pole induction machine, assume that stator windings have number of effective turns as Ns, the resistance of the stator winding be Rs and the leakage inductance of stator winding be LLS and the self inductance of stator winding be Ls. Next, for the rotor windings, we have the number of effective turns as Nr and the resistance as Rr and leakage inductance as LLR and self inductance as Lr. Theta here is the angular displacement between the stator and rotor axis. These are the voltage equations corresponds to the stator and rotor. In this, VAS, VBS, VCS are the stator voltages, IAS, IBS, ICS are the stator current, VAR, VBR, VCR are the rotor voltages, IAR, IBR, ICR are the rotor currents. Lambda AS, lambda BS, lambda CS are the stator flux linkages and lambda AR, lambda BR, lambda CR are the rotor flux linkages. Here, the rotor variables that are referred to the stator by considering the turns ratio of the winding. To solve these voltage equations, we need to know the flux linkage of each winding. Since there are 6 windings, one winding will be linked not only the flux produced by its own winding current, but also the flux produced by the current flowing in the other 5 windings. For example, let us consider lambda AS winding. So, this lambda AS winding is equal to lambda AS, lambda AS BS, lambda AS CS plus lambda AS AR plus lambda AS BR plus lambda AS CR. Here, lambda AS represents the flux which is produced by the current flowing in current IAS flowing in the AS winding, and lambda AS BS denotes the flux which is produced by current IBS flowing in the BS winding. So, like this we can get all the 6 fluxes. The inductance is defined as ratio of flux linkages to the currents generating the flux. The 6 flux linkages in stator and rotor windings can be shown here. If you represent this in the form of a matrix, these are largely divided as LS, LSR, LSR transpose and LR, where LS and LR represent the inductance matrix of stator and rotor windings and LSR represents the mutual inductance matrix between the stator and rotor windings. The stator inductor matrix consists of self-inductance of each stator winding on the diagonals and mutual inductance between the stator windings as non-diagonal elements. Here, the stator self-inductances LAS, AS, LBS, BS, LCS, CS equal to LLS plus LMS, and the mutual inductance LAS, BS, LAS, CS, LBS, AS, LBS, CS, LCS, AS and LCS, BS is equal to minus half LMS. So, like this you are going to get the stator inductance matrix. Similarly, you are going to get the rotor inductance matrix, and next you are also get the mutual inductance matrix LLR. Now, if you see the final expression, this is the final matrix which is showing the flux linkages in case of induction machine. Now, the voltage equations shown previously are converted into the DQ reference frame by using these equations. Here the DQ reference frame is rotating at a speed omega. These are the flux linkages in DQ reference frame for stator and rotor windings. In case of stationary reference frame, the omega is equal to 0. So, substituting omega equal to 0 in the previous equation results in the D component voltages and Q component voltages of stator and rotor, and even the flux linkages of stator and rotor for both D axis and Q axis. These are for the voltage equations and flux linkages in the stator and rotor for the rotating frame which is rotating in synchronous reference frame. And finally, if you see the torque expression is equal to 3 by 2 P by 2 Lm by Lr into lambda dr IQS minus lambda qr IDS. Now, if you want to apply this vector control for this induction motor, now we need to understand this basic concept. The instantaneous torque of the motor is expressed as the cross product of magnetic flux vector phi and the current I. So, this torque is equal to K psi cross I, which is equal to therefore, the torque is equal to K psi I sin theta. Now, if you see from this expression, the instantaneous torque of motor depends not only on the magnitude of the magnetic flux and current vector, but also the space angle theta between these two vectors. Now, if you make this space angle theta 90 degrees, then this sin 90 will become 1. So, this instantaneous torque can be controlled by controlling the flux and current. This is what we do in the vector control. Now, let us apply the reference frame converting the currents IAS, IBS, ICS into IDS and IQS. Commonly, the D axis stator current is aligned as the flux producing current, whereas the Q axis stator current is assigned as torque producing current. For the assigned D axis stator current to become true flux component, the D axis should be located at the actual position of flux vector in induction motor. By doing this, the torque will becomes equal to some constant lambda into IQS. Now, by controlling the IQS, you can control the instantaneous torque. This induction machine has mostly 3 fluxes: stator flux, rotor flux and air gap flux. Among these 3 flux, rotor flux oriented control is most popular due to its simplicity. In the stationary DQ rotor flux linkages, we can see that the flux linkage angle theta I is equal to tan inverse of lambda qr by lambda dr. The D axis rotor voltage equation in synchronous reference frame is 0 equal to RR IDR plus P lambda dr minus omega E minus omega R lambda qr. Here P denotes the differential operator. Now, if you simplify this, the stator D axis rotor flux equation lambda dr equal to Lm into IDS. By controlling the D axis current, you can control the rotor flux. Next, if you see the torque expression, the torque can be controlled by controlling the Q axis current. This is the block diagram implementation used in the vector control of induction motor. Here we are going to sense the motor currents IAS, IBS, ICS, and next you are going to calculate the theta from QR and DR. Next, the reference IDR is obtained from the rated flux by Lm, and the reference IQS current is obtained from the rated torque divided by a constant K. Using this transformation, we can get IAS star, IBS star and ICS star. These are compared with actual values by using a current controller, and gating pulses are generated for the inverter. In this way, you are going to apply the field oriented control of induction motor. With this, I am concluding the today's lecture.